Dr. Sujata N. Patil, Exicom member, IEEE Bangalore section, ITS chapter, working at KLE Dr. M.S. Seshgiri College of Engineering and Technology, Belgavi. Welcome you all for this international webinar on mathematical precision analysis of DSP algorithms, organized by IEEE Information Theory Society, Bangalore chapter, in association with IEEE Bangalore section and IEEE Mysore subsection. So let me start by briefing about the IEEE activities. The Institute of Electrical and Electronics Engineers is the world's largest technical professional organization dedicated to advancing technologies for the benefit of humanity. IEEE and its members inspire a global community to innovate for the better tomorrow through highly cited publications, conferences, technology standards, and professional activities. IEEE is a trusted voice for engineering, computing, and technology information. IEEE Information Theory Society membership enables an individual to stay currently updated within the chosen technology and also ensures to connect with the peers. IEEE Information Theory Society is a leading technical society that focuses on processing, transmission, storage, and use of information, as well as the foundation of communication process. So with this brief introduction about the ITS chapter, now I request Dr. Amber Bajpai, Secretary ITS chapter, Atria Institute of Technology, Bangalore, to welcome this session. And also I request Dr. Amber to introduce our today's speaker, Dr. Gabriel Caffarena, Associate Professor, University CEO, San Pablo, Spain. Over to you, sir.
Thank you, Dr. Patil. On behalf of Information Theory Society chapter, IEEE Bangalore section, I would like to welcome all the participants and our honored guest, Dr. Gabriel Caffarena. So I would like to introduce our speaker for today's webinar event. Dr. Gabriel Caffarena works as an associate professor in the Department of Information Technology at University of CEU San Pablo, Spain. He holds a Master's of Engineering in Telecommunication Engineering from University of Malaga, Spain, and a PhD degree from Technical University of Madrid. Since 2013, he is invited professor at Institut National des Sciences Appliquées, Rennes, France. He is a senior member of IEEE and served as EUROSIP local liaison officer in the period of 2010 to 2018. He has been visiting researcher at IMEC, Imperial College London, INSET, Lannion, INSA Rennes, and the University of Oxford. He has published 50 plus publications in index journals and international congresses. He has several special talks and served in the steering and technical committees of International Congress. He has co-edited special issues in journals such as EUROSIP, MDPI, etc. His research focuses on mathematical precision analysis of DSP algorithm, high-level synthesis, and FPGA GPU acceleration of scientific applications. For today's webinar title, he is going to address us about mathematical precision analysis of DSP algorithm. So with this brief introduction, I would like to over to Dr. Gabriel Caffarena. Thank you.
Thank you very much for the nice introduction. Thank you very much also for the invitation. It is really a pleasure. So I'm going to start talking about mathematical precision analysis of DSP algorithms. So in this talk, I'm going to talk about the precision optimization of algorithms, but mainly focus on hardware implementations. So the idea is that with this precision optimization, we can find the optimal precision for each operation so that we can reduce the cost while keeping the quality of the application. We will see a little bit error estimation. Also, we will review a fixed point and floating point arithmetic. And finally, we will talk about different techniques to perform precision optimization. So I'm going to start with finite word length effects. Finite word length effects normally are seen as a limitation that we have in digital systems because the numbers cannot be expressed with or represented with an infinite number of bits. So finite word length effects normally are seen as the errors that are introduced in our system, but we should also think that these effects are very important in the cost of the system because we are limiting the number of bits, which is introducing errors, but also we are reducing the cost. So if we understand the problem, we can find the right word length, the right precision for each part of our algorithm so that the cost of the system is optimized. Here we can see an example of finite word length effects. This is a simple FIR filter. We have an input X, we have two delays, D1, D2, and three constant multipliers. The constant multipliers are multiplying the input by a coefficient, an 8-bit coefficient, in this example, okay? The input has also 8 bits, but at any point in our circuit, we might decide to reduce the number of bits. For example, here we are using 7 instead of 8. So this is clearly affecting the area of this multiplier. So we could say that if we use generic multipliers, this multiplier will be smaller than the other. So you see, reducing the number of bits has a clear effect in the cost. Now, at the output of these multipliers, we might decide also to reduce the number of bits. If the input is 8 bits and the coefficient has also 8 bits, the output should have 60 bits, but we might decide to reduce that. Okay. Now, these decisions are not easy to make, and the goal is to reduce the overall cost while keeping the good enough quality. Now, let's have a look at what is happening here when we put a 7 here or a 9 here, for example. What we are actually doing is to quantize the signal. So we are reducing the precision here from 8 to 7 bits, and for example here from 15 to 9 bits. So this reduction in the precision is introducing an error. So in this circuit we have 1, 2, 3, 4 sources of errors. And of course, those errors are going to affect the quality. So the error is related to the number of bits that we are removing from the signal, but also is related to the path that error is following to get to the output. So for example, error 1, we can see that is passing through this multiplier. So the effect of error 1 at the output is error 1 times coefficient B2. So depending on the value of B2, we will have more or less noise. Okay. For example, error 3 is going straight to the output. So error 3 is directly reaching the output. So all these variables that we have here makes precision optimization a quite complex problem. How do we deal with precision optimization that you will find in the literature that has many names, like quantization, word length refinement, sometimes fixed point refinement, if it is applied to fixed point arithmetic, and so on? What we do is to divide the optimization in two parts. The first part is the dynamic range analysis, where we analyze the range of signals. So from there, we can obtain the range of exponents if we are dealing with floating point. So with the range of exponent, we know the number of bits that we need for the exponent. Or we can check the location of the fractional point. This is interesting for fixed point. And eventually, once we know this, the range of signals, we start an optimization process that is called word length optimization, where many different combinations of word lengths or precisions are tested. Okay, I didn't mention that word length is the size of each signal and is directly related to the precision. The bigger the word length, the bigger the precision. So eventually, we will get the word length that minimizes the cost. If we have a look at the word length optimization process, there is an optimization control block that is the one that decides about the changes, the variations in the word length. For each variation, we have to test the error. If we have to test if the error complies with the specifications, and also we need to estimate the cost. With the error and the cost estimations, we can steer the optimization process. So as you can see, this could be a very long process where many estimations must be performed. The precision optimization, therefore, is a very long process. It could take up to 50% of the design process. So it would be really great if we can reduce the time it takes to do this estimation of the error and the cost. Mainly the error, because the error estimation is quite very time consuming. About the cost, normally precision optimization is performed at a very early stage in the design process, so it's very difficult to have a good model of the hardware architecture. So sometimes we resort to rough estimations of the cost, like power, area, speed, etc. But as I said, the main problem here is the error estimation. Yes. Sorry about that. I think. Sorry about that. I don't know why it's using this audio file. I didn't check to reproduce the audio, so I'm going to just give me 1 minute. I'm sorry, really sorry about that. I'll check if this is happening again. Okay, it's not happening. The mystery. All right, so we can perform this error estimation by means of bit-true simulations or fast analytical estimation. I'm going to concentrate only on noise power here. There are other analytical techniques, for example, to estimate the peak value of the error or bit error rate. Well, okay. So these are the main approaches. Bit-true simulations are interesting because they are universal in the sense that we can apply bit-true simulations to any kind of system. And they are based in this idea of simulating the effects, the finite word length effects of our algorithm bit by bit. Okay, so they are bit-true. That's the name why they are called bit-true. They are very time consuming because we need to run very long simulations. We have to be very careful with the input vectors that we use. They have to cover the most important possibility. So the idea is that we perform with the same input vectors 2 simulations. One simulation is normally performed using floating point with a high precision, could be double or quadruple. And this will be our reference. We need to run the simulation only once. And during our word length optimization process, we had to test if the bit-true simulation complies with or is similar to the floating point simulation. For the bit-true simulation, we can decide to use fixed point, arithmetic, or custom floating point. And we can use the fixed point toolbox from MATLAB, or, for example, the AC type library from Mentor Graphics, or a multiple precision library GNU library. And eventually what we get is the difference between these two simulations, and we can obtain the power of the noise, the signal to quantization noise ratio, the maximum error, the difference in the bit error rate. Okay, but the thing is that this is always safe. We can use it for any kind of system, but it is very slow. Regarding analytical models, and in the context of noise power, we can estimate the signal to quantization noise ratio applying this formula, where the ratio between the power of the signal and the power of the quantization noise is involved. So these analytical models, they allow us to have an expression from for the output noise. And that expression is a function of the word length. So this is a very fast expression to compute. And it is based on this idea that we can replace each quantization by an additive white noise with uniform distribution. This happens when the power of the signal is much bigger than the power of the noise, or the size of the error. And as you know, in LTI systems, the white noises, they have very nice properties, and it's very easy to estimate the effect of their statistical parameters at the output of the system. So the whole idea, if we apply these analytical models to LTI systems, to linear time invariant systems, is this. Instead of using quantization, what we do is to replace the quantizer with an error that is added there. And in order to propagate that error to the output, we compute what I call the local impulse response, which is the impulse response from the quantization point to the output. So now, if we have the impulse responses for all the signals in our system, we can obtain the variance of the noise at the output and also the mean of the noise at the output as a linear combination of the variance of each individual noise and the mean of each individual noise. The only thing that we need is the input responses that, as you can see here, they appear as constants that are multiplying each variance and mean parameters. These constants, we can call them the noise gains. The nice thing about these constants is that they can be pre-computed before doing word length optimization. So if we change the word length of one signal, we are changing the variance and also the mean, but the noise gains will be constant. Okay, so now what we do is, before running the optimization process, we analyze the graph to obtain the noise gains. And during the optimization loop, we can call a fast error estimation, that is this function that I just showed you. So the only thing is that we need to perform a word length propagation to be sure of the exact word length of each signal before applying the models, because we want these models, these estimators, sorry, to be as accurate as possible. But with this idea, we can accelerate the word length optimization even 3 orders of magnitude in comparison with Vitro simulations. Now, this is applicable only to LTI systems, but there are some works where we can compute noise gains for, let's say, quasi-linear systems, the so-called smooth operators. We can obtain a pseudo input response. I'm not going to explain this. So it is possible to apply these fast models also to adaptive filters, or I don't know, matrix multiplications, algorithms like that. The only problem is that the pseudo input response depends on the input vectors. So this is similar to somehow to Vitro simulations. We have to be very sure about the input vectors that we use to obtain the noise gains. Okay, so this is just an introduction to the problem we are addressing. Now let's talk a little bit about fixed point and floating point. In a general way, we can say that fixed point is used when we want to have very efficient hardware, low power, fast, low area. It is suitable for signals with a small range, and it could be a headache for the designer because we have to deal with the alignment of different signals. So if we use a different precision for each signal, the location of the fractional point would be different, and we have to handle that. As for floating point, they are actually the dual format. It is suitable for high dynamic range of signals. The alignment is performed automatically, but that implies more complex hardware because the alignment is done through the operator, through the hardware. And that means that because the hardware is more complex, it could be not as fast and not as low power as fixed point. So I'll give you some numbers. You can see here we have the energy consumed by fixed point operations and floating point. And you can see that the energy could be, for floating point, be one order of magnitude higher. So one might think that fixed point is always the best solution for low power. However, the really interesting thing would be to be able to optimize system simultaneously or in parallel, checking if fixed point or floating point are the best solutions. We have this nice work from 2011 where they implemented communication systems using a 12-bit floating point CPU and also a 16-bit fixed point CPU with the same results. Similar area, similar power consumption, and similar speed. So you see, this should be an interesting goal to be able to decide which is the arithmetic that fits best our system or our goal. Now let's talk a little bit about the format of fixed point. In fixed point, we have the numbers have a mantissa of n bits, time bit, and there is a fractional point, and we use this parameter n for the mantissa and p for the location of the sign bit. So basically, p is always the weight where the sign bit resides. Here you can see two examples, two different numbers with different formats. You can see that we can have numbers with no integer parts, or well, in those two examples. Now, if we know the parameters, the fixed point parameters p, n, and also we know the sign and the mantissa, we can obtain the value of the fixed point number using that formula. Just bear in mind that p and n is fixed. So for each signal, the format is fixed. Now, I'll give you an example, and this is the problem I mentioned before that is a headache for designers. We have here another. We are simply adding a plus b, but the formats of a and b are different. This is a, okay? This is b. So before doing the addition, we have to be sure that all the bits in these signals are aligned. So as a result, the value of the output signal of the other has a bigger number of bits. It doesn't have 4, it has 6. And after that, we might decide to reduce the number. I put 4 here, but it could be 5, it could be 3. So you see, while we are doing this operator that is so simple, a plus b, we have to think about alignment of everything, of the inputs, and also how we are going to deal with the output. And also, this is very common in additions. Sometimes we are reducing just a few bits. So this is not when we think about quantization, sometimes we think of a lot of bits that are being removed, but sometimes it's just a few bits. It could be 1, it could be 2. Okay. Right. So we have very nice statistical models for fixed point. And this one here at the bottom is the one that we normally use. If we want to quantize to NQ bits, we use this formula. Okay, for the variance, for the mean. This is, we could say, exact for analog to digital conversion. But when we are removing just a few bits, this formula is not enough. We need to resort to this formula that is a little bit more complex. Here we are considering the previous word length and the final word length, mprev and NQ. And as you can see, mprev, the previous word length, has an important impact. If we reduce just a few bits, but we use the traditional model, we might be incurring in an error or 100% of the power of the noise. Okay, so this is complicating even further the optimization of this system. Now we can also, I was assuming truncation, meaning that we just remove the bits, but if there is rounding, traditional rounding, we get the same equation for the variance, but we have a different expression for the mean, and the mean is not zero. Okay, this is another assumption that we always make, that the mean of rounding numbers is zero. This is only true maybe for round to even in floating point, or so. But the traditional rounding, the mean is not zero, so we have to consider that also when we propagate the noises around our circuit. Okay, actually, well, this is not. Sorry about that. I don't think this is completely true. The mean is not zero in general, but if mprev is very big, we could consider that it's very small. Okay. So now, if we want to obtain the value, the numerical value of a floating point number, now the big difference is that we have a mantissa with n bits, but the mantissa, the value of the mantissa has an implicit one. We all know that. There is also a sign, and now another variable is the exponent. Okay, so I'm not considering here that we are quantizing the exponent, only the mantissa. So the mantissa has n bits, and it is a very interesting idea to apply custom floating point, which is that we can use any number for the mantissa and the exponent. We move away from the standard, from the IEEE standard for floating point, and we can do that for the sake of reducing the cost. Now, the errors occur in additions every time the two inputs are misaligned. So if they don't have the same exponent, there will be an error. Also, if there is an overflow in the mantissa, we have to normalize. And in multiplications, we will have always a quantization errors, because the number of bits at the output of a multiplier is always bigger than the number of bits at the input. So it will be bigger than the mantissa, at the word length of the mantissa. So it would be really great if we can obtain a statistical parameters similar to the ones we have in fixed point, to apply these fast estimators during word length optimization. So what we do here is to consider the following. Every time there is a floating point operation, there is a truncation. Well, there could be a truncation in the mantissa. This truncation is dynamic because it depends on the current values of the exponents. If there is, we have to normalize if the numbers are aligned, etc. So if there is a quantization, we can see that quantization as a fixed point quantization. So we are simply quantizing the mantissa. We can see it as a fixed point number that is 1.m. And then we have the exponent. The exponent is scaling the number. So we can see the floating point quantization noise as a floating fixed point quantization noise. So if we do that, if we perform the statistical analysis using this formula, that the error in a floating point signal is 2 to the exponent of the signal multiplied by the multiplied by the error of the mantissa that I'm calling here the fixed point error, what we get is the following. If we apply round to even, the mean is 0, and the variance is the variance of the quantization of the mantissa, the fixed point variance, multiplied by the power of 2 to the exponent. So there is one part of this quantization noise that is related to the signal, and another part that is related to the word length. Okay, so now that we have an expression for the mean and the variance, it is possible to apply to compute the noise gains and apply fast estimators. So first of all, we perform the computation of the noise gains, and then we compute the power of 2 to the exponent for each signal. And after that, we can apply a word length optimization. So the nice thing is that now we have a fast method, and the drawback is that there is one part of the statistical model of each noise that depends on the signal. So we have to be careful about the inputs that we use to obtain the power of the 2 to the exponent. Okay, so but well, the good news is that now we can use the same ideas for fixed point and floating point and have a fast estimation of the error. Okay, I'll give you an example. This is a toy example, a very simple example, where we are multiplying by a constant k, a signal, and at the output we have a number of bits. This could be the bits of the mantissa of floating point, or it could be the bits of a fixed point number. And we are reducing the number of bits to NQ. So if we compute for different values of k, the noise of the power of the fixed point quantization noise, we get, this is an empirical result, we get more or less the same value. You can see that it's around 1.27 10 minus 6. However, in floating point, because the error, the quantization error, depends on the exponent, and the exponent, we can affect the exponent changing the value of k, because we are making the signal bigger. The error is increasing. The power of the error is increasing with the value of k. This is case 1 up to k15. So what I'm trying to point out here is that the optimization process would be very different in fixed point and floating point. So we cannot reuse ideas or the optimization from fixed point. We cannot reuse it in floating point. It's a completely different paradigm. Okay, now I'm going to show you some techniques to optimize these systems. I have divided these the approaches in 2 main blocks. This is one block in green here. That this block, these are very, let's say, sophisticated algorithms. They require a very long time. Well, it's not really that they are sophisticated. Some of them are. Some of them are just a brute force. But if we want to reach an optimal or quasi-optimal result, we need to perform lots of iterations, or we need to apply time-consuming numerical methods, like linear programming, for example. However, we have also techniques that they reach a solution in a much shorter time, but some of them, they produce not very, solutions that are far from optimal because there are local minima, and some of them are very good. So in general here, we have linear programming, check all possibilities, check possibilities, but constraining the combinations. And of course, we have the stochastic optimizations like simulated annealing. where there are some random movements involved. We have the gradient descent or ascent techniques that are very easy to implement, and they are fast, but they can get stuck in local minima. And finally, we have this very interesting idea of applying real, assuming that the word lengths are real numbers, so we can have fractional word lengths, like for example 8.3, okay, 8.3 bits instead of 8 or 9. So we can apply numerical methods considering that the word lengths are real. That means that the execution time will be faster, because when we optimize a real problem, it's faster than optimizing a problem that is expressed with integer variables. Now, after obtaining those real word lengths, it is necessary to truncate or to round those values to obtain feasible numbers. So it is really nice because we can obtain quasi-optimal results. Okay, I'll give you just an example of gradient descent. I told you that gradient descent is easy to implement and it's also fast, but there is also an explosion of combinations here. The main idea, as you know, is to start with a solution and then analyze the gradient of each change that we perform in our variables. So we start with a uniform word length. In this case, it's just an example, 16 bits. We assume that with 16 bits, we reach good enough quality. And then we start testing each individual change in a variable. So we reduce this variable to 15, this variable to 15, this one and this one, as you can see. So we have to perform many simulations, many estimations, and we get the best candidate. The best candidate is the one that reduced most the cost, or the one that produces less error. There are different alternatives. But the point here is that at each step, we are testing many, we have to test many combinations, because we are reducing only one signal, one unit. So even though for such a simple algorithm, there is an explosion in iterations. Just to give you some numbers, very simple circuits or algorithm like a fourth order infinite input response filter requires 300 iterations, and a fifth order LMS filter, an adaptive filter, requires 6,000. So you see, even such a small circuit, they require lots of iterations. Now, about simulated annealing, the idea is to pick up at random any signal and to perform a random change. We could increase or decrease the size of the word length. If the result is positive, if the cost is reduced, the change is accepted. If not, it's accepted with some probability. So we accept decreasing the word length with a higher probability than increasing the word length, because it is increasing the cost. So if we apply gradient descent and simulated annealing to an 8th order FIR filter, you can see that we obtain very nice results. We can reduce the cost 45% using gradient descent, or we can reach 62% reductions using simulated annealing. But of course, simulated annealing requires a huge amount of iterations. Okay, so what can we do to accelerate these optimizations? We can resort to hardware acceleration. We can use fast estimators. So I explained that before. We can use the continuous domain approaches, seem to work very well, or we can use hierarchical approaches. So I'm going to talk a little bit about hardware acceleration. For example, we can use GPUs. I tested this myself with gradient descent. So the idea is that instead of running, if we have, let's say, if we have a number of signals, let's say n signals, instead of doing n simulations, we perform a single GPU simulation that is doing the N simulations in parallel. It is possible to do that with the GPU. So instead of, I mean, we are considerably reducing the number of simulations by doing that, and we reach a speed up of 60. So now our optimization goes 60 times faster thanks to that. Another possibility is to use FPGAs. So we can implement our algorithm in an FPGA using hardware, and before each input of an operator, we can put what we call a precision limiter. Okay, so we have a PC that is running the word length optimization, is taking all the decisions, and is talking to the accelerator and asking the accelerator to reduce the bits or to increase the bits of particular signal. Okay, so there is some protocol here, some communication between the PC, the accelerator, and then the accelerator is affecting the size of a different word length. But the nice thing is that once the circuit is implemented, we can run all the simulations one after the other very, very fast. We have this is a work I do in collaboration with Dr. Romigo from University of Malaga. We presented that pretty soon in ARIF 2021. Okay. Now, I would like to talk about this work by Novo et al. From 2013 about hierarchical approaches. Because so far we've seen that we apply this optimization to algorithms, but when the algorithm is very complex and it's maybe it's not really an algorithm, it's a system, there will be an explosion in the number of variables and the number of iterations. So it is the only solution, the only practical solution that we have is to subdivide the problem. So there are several hierarchical approaches, but I'm going to explain this one because I think it's quite representative. So imagine that we have our system already divided in blocks, ABC in this example. So in this paper, they quantize or they optimize a communication system. Okay, so the quality is measured in with the bit error rate metric. So what they propose is to find the maximum Gaussian noise that we can apply at the output of each block. So first of all, we start individually. We apply, we increase the power of this noise until the bit error rate is degraded. So for each block, we have the maximum power of the noise that the output tolerates. So we do this for A, we do this for B, and so on. Once we have that, we can now apply word length optimization to each individual block using the noise power, not the bit error rate. The bit error rate requires very long time for the simulations, while the power of the noise requires less time. So this is just this is one advantage. Now, instead of finding a single solution, they find several solutions that are close to the noise power. So they have, for each block, they have different word length sets. Okay, and then what they do is to test all those solutions, checking if they comply with the bit error rate degradation that is allowed. And as you can see here, if one word length set does not comply with the bit error rate, it is discarded. And the final step is to try all combinations of word length sets simultaneously to check if they comply with the bit error rate, and finally they get the one that produces the best cost. Okay, so this is just using your imagination with some science, some engineering in the middle. Okay, now that's all I would like to conclude. we have seen that mathematical precision analysis that I call the precision optimization is essential for the implementation of digital systems. Word length optimization is an NP-hard problem. And I have presented several ideas to accelerate this optimization with GPUs, with FPGAs, using fast error estimations, hierarchical approaches, and so on. There is still plenty of room for research. Right now in deep learning, there are a lot of possibilities for this field. Also, we have this idea of dynamically changing the precision depending on the quality of our inputs. That's also a very interesting research line. We can check for new arithmetic formats. Approximate computing now is also quite hot. Again, we can find out new ways to optimize or new ways to apply optimization with different strategies. There is lots to do in fast error models and so on. So, well, it's really nice to be able to be so close, even though we are so far away. These are my emails if you need anything. I would like to thank you and also to answer any questions that you have. Thank you very much.
Thank you very much, Doctor. It's Gabriel. It's fantastic listening about the hardware algorithms for support of implementation of some of the most advanced approaches in deep learning and has impact on FPGA and other development. I remember having been to Bilbao, and then I was there for supporting a telecom company there, and interesting memories. And yes, Gracias is something that we use there, and
yes.
And so we wish to know from you, sir, are you open to collaborate with researchers from India on any of the future research programs, funding programs or something?
Yeah, sure. That would be very, very interesting.
And as I understand, these algorithms work only when we hard code them at the hardware level. But FPGA allows for certain flexibility to make the changes to the code. Have you come across use cases where it can be used for UAVs or drones or any such implementations where security is required to be very important at the hardware level itself, so that we will not see some of the rogue drones or some unforeseen things from the drones that are likely to be more in number in coming decade. So there's a lot of risk associated if we don't do security at hardware level.
Okay, but I would like to point out that this precision optimization, I focus on the implementation, the hardware implementation, but it's also applicable to embedded system, where we have to decide about the data types. We could use 8 bits, 16 bits, 32 bits. So applying this optimization is also interesting for that. We can use it also in FPGAs, but also in ASICs, integrated circuits. So, but I'm sorry, I didn't get the final part of the question because you were talking about security, but I didn't.
Yeah. So
didn't get it.
Yes, one of the possible threats that has been identified is from drone. If somebody can do some modifications and and fake the government authorized codes, and they have some malified intent. To prevent such things at the hardware level of the design of the flight controllers, there should be certain mechanism with which the regulator should be able to monitor all the changes, and that can be done through only hardware, that is at the FPGA level or ASIC level, as you said.
Okay, I see.
Thank you very much.
Thank you. Thank you.
So there are few questions in the chat window. I would like to read for you. One UG student asking that what kind of practical applications included in optimization in computer fields?
Okay, but I don't know if the question is about if the optimization ideas that I'm presenting here can be applied to other problems. Is that so?
Rupini, if you can unmute and answer, please ask your query if you are present.
I'm saying that because yes.
Yeah. Yes, sir.
No, yes, optimization. I mean, it's a general. I mean, we are always optimizing something. Here we are optimizing something very particular, which is the number of bits, and there are some constraints. We cannot just. There is a dependency between the different changes that we perform in the signals, in the wavelengths of the signal. So this is a very particular field, and some of the conclusions that we got here cannot be applied to any other to other fields. However, things like hardware acceleration, that could be very interesting. If you are working on optimizing a problem, and optimization is really something that you have to do many times. For example, here is something that we do every time we design a circuit. We have to go through this optimization, wavelength optimization part. So if we can generate a hardware system to do that very fast, we can accelerate it. That's always interesting, and it could have also an industrial impact. So for anyone working on optimization, in many cases we can use GPUs, but in some cases, maybe GPUs are not the best option. And maybe thinking of creating a circuit in an FPGA to solve the optimization problem could be a very nice idea, especially if this is something that is used and it could be integrated in industry.
Thank you. I hope the students got the answer. So another question is from Sri Vidya. Can you unmute, because it is not much clear to me. So if you are there, she's asking for some research problem she's facing to quantify the real-time complex signal. Can you unmute, please, and ask your query?
Sure, sir. Sure, sir.
Please go ahead.
Sir, first of all, I would like to thank you for giving such a very nice presentation. So my question is, like, when we are trying to quantize the real-time complex signals, then the quantization output would be almost looks similar. But what I'm looking out for is the outputs which are not statistically related, or the outputs, how can I get a varied range of outputs during the quantization method? That means which kind of quantization would be better?
But I mean, so you're saying that you have some outputs,
complex signal, yes,
yes,
and that if I quantize into zeros and ones, so I am almost getting the similar kind of outputs which are related to each other. So I want independent outputs, means which quantization techniques can I use to get a different kind of outputs.
So you are going from real numbers to binary, to quantized numbers?
Yes, sir. Yes, sir. Yes, sir.
And but I don't understand the independency that you are mentioning between the outputs.
Yes,
It's
sir.
something that should be there even from when they are real.
Yes, sir. Yes, sir.
But I
In the
don't.
real, they are related. In the real,
Yes.
they are related. But after quantization, the output should not be statistically related. Can I achieve using any of the quantization technique? Any suitable technique is there, or should I use a separate technique for once again making it statistically independent?
Okay, but maybe the things I was talking about are signals. It could be, for example, audio signal, images. It could
Yes,
be physiological signals. Okay, and we are trying to lose as less information as possible during the quantization. But maybe you are talking about coding. I don't know if you are
yes,
if you are talking about that.
yes, sir. Yes, sir.
But
Yes, sir. Yes, I'm talking about that. Yes, sir.
yes. So maybe it's a well, I think it's a completely different point of view. So because
Okay,
what I tried here was to actually lose just the right amount of precision of information, but not really transforming the signal into something different, which is something that maybe you need, and maybe that quantization is more from the information theory point of view.
Yes, sir. Yes, sir. Yes,
So you see, so I think I cannot give you an answer with the techniques I explained here.
Okay, sir. See, my problem
Anyway,
was like if
yes.
I round the values, it is almost coming similar. That's what I was worried.
Okay.
Okay. Anyway, sir. Yes, sir. So when we round the value to the nearest one, so almost the output looks similar. So
yes.
How,
But
yes,
then,
so how to? Yes, sir.
But you said that you wanted to be the outputs to be independent.
Yes, sir. Independent and different from previous output.
Yes, but there is a step there that I'm missing. That you need to transform the signals somehow. It's not really related to the quantization method that you use, I think. Anyway, I will be happy. Please
yes,
don't mind
I'll
at all
write to you,
if you can write to me and I could check it with more detail.
Definitely, sir. Definitely, sir. I'll write to you. Thank you for your patience, sir. Thank you.
Thank you very much.
Professor, another question I would like to read for you from Dr. Anita. She's asking, what is the need for developing WL optimization on HW, while it is a one-time process which can be handled on the software?
Can you say it again, the application?
Okay. She's asking about the need for developing WL optimization on hardware.
Yes. The need.
Yeah.
Well, it's you have to do it always. So if you don't do that, I think I can answer the question. Just looking at this slide. If we go for a very simple approach where we take all the signals and we use the same precision for all of them, the same number of bits, we are here in the uniform word length solution. And after optimizing, we can reduce the cost. We can reduce it 45% or 62%. So you see, it's really important to do it, because if we are able to have a system that is a third of the size, or maybe a third is consuming third of the power of the original system, this is the way to really produce a commercial and a feasible product. So it is essential. We have to do it always. Every time we want to do hardware, we need to think about the word length optimization. So it's not optional. Otherwise, you will get an implementation that is huge and that is not efficient. Okay, so that's the answer.
Professor, can I reframe my question?
Yeah, please, Dr. Anita, you can reframe. Please go ahead.
I think software is good way of doing word length optimization than hardware. So why should we choose hardware to for word length optimization than over software?
Okay, sorry. I thought that you were talking about in general. Yes. When we perform simulations using software, we have to model the limitations in the operators, in the hardware operators, using software instructions. For example, if we want to simulate an operator that is multiplying inputs with 7 bits, there is no such an operation in a CPU. It could be one with 8 bits, or well, sometimes we don't have a small operations. Normally we have 32, 64 bits. So we have to implement, for example, to deal with 7 bits, we have to remove from the word that the CPU uses, we have to remove the rest of the bits, applying a mask, doing an operation. Also, we have to deal with alignment. So if we want to emulate or to simulate the other that I explained before, and we have to the numbers have different format. We have to shift the values in order for them to be aligned. So we have to do the aligned using software instructions. Okay. So in this idea I presented here, we have the hardware operators implemented directly in our FPGA, and we have these masks to limit the number of bits automatically as a hardware operator. In software, you will need to have a software instruction to do this masking, a software instruction to do the shifting, and the same for the result. So we can overload the operators, so it's nice to use, but it's not very efficient. We need to perform a lot of operations per hardware operation in our system. So that is the reason to implement in hardware the word length optimization. But we still have to prove it. Okay, we are now about to present it, and we still have to prove that this is a feasible solution. And of course, if the algorithm is very complex, it has lots of signals or variables. Maybe we don't have enough memory, enough capacity inside the FPGA, or enough memory to deal with all the variables, with the input vectors, and so on. So the thing is that this is not commonly done by hardware. It's most of the time by software. So I don't know if I answered your question.
Yes, Professor, thank you.
Thank you.
Now may I request Dr. Patil, since no more questions, to proceed for concluding remarks and vote of thanks ceremony.
Yes, sir. Am I audible, sir? Hello?
Yes, madam. Yes, absolutely. You are audible.
Yeah, thank you, sir, for the nice presentation on mathematical modeling with the DSP algorithms. So now, may I request Kishore, sir, to propose vote of thanks?
Thank you. And it's my honor and pleasure to propose vote of thanks for the speaker of the day, mathematical precision analysis of digital signal processing algorithms, Dr. Gabriel Caffarena. And in fact, the conversations which we had with professors, for instance, on generating mutually exclusive codes, I think is after this talk also we would take your support. Probably that professor is trying to generate some mutually exclusive codes like Walsh codes, which are used in communication. And probably we could take your help, as you said, by transforming. So I think your talk has generated research interest, apparently from many of our research colleagues. And as always, IEEE ITS is doing a great job to the community by inviting speakers from across the globe. And every evening we hear speakers like you said. We are really blessed during these difficult days to spend time productively and then focus on things that matter, because that's ultimately what we are all supposed to do as knowledge workers, to spend time productively and give back to community. So I'm also very happy that you are open to collaborate with the researchers in the region. So looking forward to some collaborative engagement with you, and very nice mathematical. In fact, that is where we cannot separate the some of the fundamentals that we know, like mathematics and physics and electronics. They are all inseparably interconnected. So the benefits of them would be leveraged to all the products and services. So we make a very robust, secure information technology products that would help the humanity. And especially DSP and these algorithms will go into the electronics. And India is now eagerly looking forward for becoming the electronics giant, just like China. So we are hoping that more and more interactions with you, and such topics are of most relevance for all our professors and industry partners. Thank you very much, and thanks IEEE ITS, Dr. Params and Dr. Sujata and the entire team, Dr. Amber, for continuing to inspire the IEEE intellectual community to have this kind of short 1 hour webinars. I'm looking forward to hearing you more from you also, sir, in the times to come. Thanks a lot, Dr. Gabriel.
Thank you very much. Thank you very much. It's been a pleasure and an honor, actually, and I will be delighted to collaborate. And also, I would like to send you my best regards. And
Yes,
I
sir.
hope that things get better
Yes.
pretty soon. I hope so.
Thank you,
Sir,
Professor.
Thank you. Thank you. Thanks for the nice presentation. We'll see you.
Thank you, Doctor.
Take care.
Yeah, thank you. Thank
Thank
you,
you,
Professor.
Dr. Params.
Thank you. Kishore sir, thank you. Sir,
Thank you.
Kishore sir, you submitted that you got that.
Yeah. We are still we are progressing, and we have some more to do, and I'll connect with you on that.
Okay. Okay. Thank you, Professor. Thank you. Bye-bye.
Thank you, Dr. Gabriel, for
Very pleased
Thank you,
to meet you all. Very pleased to meet you all.
Thank you,
Thank
sir.
you.
Thank you.
Thank you, Dr.
Take care.
Param,
Gracias.
for the original invitation.
Thank you, sir.
Gracias.
Okay,
Thank you.
I will
Thank you
disconnect
all.
now.
Thank you all the
Thank you very much.
participants they have joined. Thank you all. See you in the next webinar.
Thank you, sir.
Thank you, everyone.
Thank you all.
Thank you, Dr. Param.
I thank all the execom members of ITS chapter. Thank you.
Thank you, sir.
Okay. Bye-bye.
Bye-bye, sir.